Okay, so remember last time we talked about oh, I think you need to be muted there, Owen. There you go. I'll mute you. Last time we talked about parent functions, and I gave you a whole list of parent functions. Oh, you guys can't see you can't see my screen, can you? There you go. So we talked about the graphs of all those parent functions, right? And you guys are working on an assignment about that, about just kind of memorizing what those all look like. So today we're going to look at what can we do with all those parent functions? How can we transform those very basic parent functions? Okay, we're going to start off looking at what happens if we add or subtract a number directly to x inside the function. Okay, so if we start off with some function f of x, and then what happens if we add the number h to x inside the function or subtract the number h from x inside the function? Let's explore that a little bit. Whoops. Okay, so what if we start off with the parent graph, p of x equals the absolute value of x. So there's our v-shaped parent function. And then let's see what happens if we subtract some number from x inside the function. So and why don't you guys make a prediction for me here? It's kind of a guess. I mean, we haven't talked about this yet, so don't be worried about getting this wrong. But what happens if I turn that h into like a 3? So now I've got this new function f of x equals the absolute value of x that we're starting with, but the absolute value of x minus 3. What's that going to do? So our new f of x function will be red. Well, right now I'm subtracting 0 from x, so it hasn't done anything, right? But what happens if I subtract 3 from x? What do you think that's going to do? Okay, so I'm getting some guesses here. The y-intercept will move, okay. Turns into a negative slope, I'm hearing. Anyone else want to make a guess on this? New starting point. Okay, so new vertex. Okay. Be more specific. For those of you who are saying that it's going to move, where, in what direction is it going to move? These are total guesses. I mean, I get these are total guesses here. Up 3? Let's find out, huh? So what happens if I subtract 3 from x inside the function? So I'm going to turn the h into a 3. Whoops, there's a 3. Look what it did. Subtracting 3 from x moved it to the right by 3. Okay, what about adding 3 to x? Well, how do I add 3 to x? That'd be the same as subtracting a negative, right? So if I make h a negative number, like negative 4, x minus negative 4 would be the same thing as the absolute value of x minus 4, right? Here, I'll prove it to you. Y equals the absolute value of x minus 4, or sorry, plus 4. Look what it did. Put it right there. That moved it, adding 4 to x inside the function, moved it to the left by 4. Okay, that's kind of backwards of what we probably would have expected, right? So adding h to x directly to the x. So I'm replacing the x with an x minus h, moves it left h. Subtracting h directly from x, darn it, moves it right by h units. What do you suppose it does if I add k outside of the function? Make a guess on that one. What do you think? Type it in chat for me. So here's my parent graph again, the absolute value of x. Now, what's going to happen with f of x when I add k outside of the function? Not inside, outside of the function. Okay, Tony's saying up 3. You guys buying that? Okay, sounds good. It looks like you got some buy-in on that, Tony. Let's see what happens. Sure enough, that's what happened. Okay, so the number that I add outside of the function tells me how far it's going to move vertically. If I add a negative number, same as subtracting a number outside, it goes down. Okay, makes sense. All right, so far so good. So adding k shifts it up k units. Adding negative k or subtracting k shifts it down k units. And then we could do both of these at the same time if we wanted to, right? I could do both of these. Like if I were going to, for example, let's say I'm going to replace f of x with, how about this? I'm going to change this. I'm just going to type in something. How about if I just do, instead of x squared, I'm going to go down and inside the function, so I better put that x in parentheses because I'm squaring the whole thing. What happens if I add 3 to x inside the function and I add 4 to x outside the function? You guys make a prediction. What's that going to do? Make a prediction. What's that going to do there? So I took my regular parent graph, x squared, and I added 3 to x inside the function, and I added 4 outside the function. Okay, so left 3 and up 4. That sounds good. Sure enough, that's what it did, isn't it? Look, we took the vertex and we moved it 3 to the left and up 4. There you go. Everybody good with that? Okay, all right. So another way of thinking about that then is that h, the value of h, which is the number that we're subtracting from x, that's telling us how far we're shifting it right. So if h is negative, right, then that means I'm shifting it right to the negative by a negative amount, which is the same as going left, and k is the amount that we're shifting it up. Okay, everybody good with that? And so once again, I want to look at this just one more time real quick. So then if I let h be something like, if I start off with g of x is f of x minus h plus k, if I want to move this thing to the left, I've got to subtract a negative value of h, right? So I'd let h be negative 4. And if I want to go down, I'm going to subtract, like if I want to go down, if I want to go up by 2, I'll add 2 outside the function. Everybody agree? So that should be the same thing as saying the quantity x minus negative 4. If h is negative 4, h is the number that's being subtracted from x. So x minus negative 4 squared plus 2. Everybody agree? Look what it did. That worked, didn't it? Okay, well, minus negative 4 is kind of dorky. Minus negative 4 is the same as plus 4. Right? Okay. Give me 1 to 5 real quick before we move on. Okay, type it in chat if you're not flashing me fingers. Okay, that's a good start. That's a good start. We're going to get a lot more practice with this. Okay, so then the other thing now is what happens if we multiply by a number outside? And so to help you get ready for this, I want to bring you back, just take a walk down memory lane here. Just go back to geometry for a second. Let's take a regular shape. Now I want to pick one that's kind of weird, so it's, how about something like that? Okay, there's my shape. There were three kinds of transformations you did in geometry that we called isometric transformations, right? You might remember this from geometry, the word isometric. Isometric meant same measurements, right? So these are the types of measurements that don't change the shape or size of the object. What were they? Well, one of them is I could translate it. I could slide it around and it doesn't change the shape or the size. Everybody agree? The other thing I could do, one of the other things I could do is I could rotate it. If I rotate it, it doesn't change the shape or size. Agreed? And then the last thing I could do, what was the last thing? Anybody remember?
Reflect.
I could reflect. Yeah, you bet. I could reflect. So I could like reflect it vertically like that, for example, right? If I reflect it, it stays the same shape or size, shape and size also. Okay, good. Okay, but there was another transformation you guys did that was not isometric. Remember, we did a dilation in geometry. What was a dilation? Do you remember?
Make it smaller.
Smaller or bigger, right? So an isometric transformation, I'm going to add something to the notes here. Isometric transformation meant same shape and size. A dilation, on the other hand, meant same size or same shape but not size. So here was a dilation, right? Remember this, doing stuff like this where we either make it bigger, we inflate it uniformly, or we deflate it uniformly. Same shape, different size, right? Okay, we're doing something similar to that with these dilations that we're going to use in algebra. Okay, if I multiply a function by a, let's see what happens. So again, I've got my parent function here is just plain old absolute value of x, right? I want to see what happens to my new function f of x when I multiply my parent function by some number outside. What do you think it's going to do? Any suggestions? Type it in chat. Reflect, possibly? Okay, that's one thing it could do. You're right. More generally, what else could it do? If I multiply by a number, like what if I make A2? Look what it does. What did it do? As I change A, look what it's doing to the function. As I go, there's 1, there's 1.5, there's 2. What's it doing? Try to be very precise in your explanation. Okay, it's changing the angles, but there's more to it than that. Look at those points that line up initially, right? Look at those, the coordinate, they've got the coordinates written on those points. If I go back to A equals 1, multiplying by 1 doesn't change anything. It's the same as the parent graph, right? But look at those points that start off with the same coordinates. When I increase the value of A, what's happening to those points? Okay, it changes the slope. True. How come it's changing the slope? Yeah, look, isn't it? It's stretching those points up vertically, isn't it? Everybody agree? When I multiply by 2, I'm effectively stretching the green function upward vertically, but only vertically, right? So it's kind of like a dilation. It is a dilation, but it is a vertical dilation only. It's not the same kind of dilation you talked about in geometry class. It's a dilation where we're only stretching it vertically, right? Everybody see that? See the difference between a vertical dilation and a general dilation, right? We're only stretching it or compressing it vertically. That's what multiplying by a does. It vertically dilates the function. So I'm going to add the word vertical here. I think that's important to include. That's not. So these aren't just dilations, they're vertical dilations when I multiply by a. Okay, let's go back to that. Let's go back to that picture we were just looking at. Well, that's not it. Well, I guess I got rid of it. That's all right. I'll open it up again. So when I let a equal 2, it stretched it out by a factor of 2. Here's a way to think about that. The vertical dilation factor a, which is what we're multiplying by the function, what it's really doing is we're multiplying that a by the heights of the points on the parent graph. I'll tell you what I mean by that. Let's look at the parent graph for a second, right? We have all these coordinates. Well, notice on our parent function, the height we consider to be how far are we moving vertically from the vertex, right? The vertex is the bottom of the function in this case, okay? So if we're giving an ant directions how to get to one of these 3 points, what about this point right there that I'm pointing at right this second, okay? To get there from the vertex, we would tell the ant, okay, you're going to go to the right by 1 and up by 1. So when we go right by 1, we could say that the height of the function when x is equal, when we've moved to the right by 1, the height is positive 1. When we move to the right by 2, the function has grown some more, and now the height is 2. When we move to the right by 4, it's grown yet some more, and now the height is 4. Okay, everybody with me? When I multiply the function by a vertical dilation factor a, what I've done is I've multiplied all of those heights. Now look at this. Instead of going to the right by 1 and going up by 1, we're going to multiply that normal height by my vertical dilation factor of 2, right? So 1 times 2 is 2. So now the new height is over 1 up 2, okay? Normally we go over 2 up 2, but now we're going to multiply that height by 2, and we go over 2 and up 4. Normally we go over 4 and up 4, but we're multiplying that height by 2 to go over 4 and up 8. Everybody agree? Okay. So what's going to be the outcome then? What's going to be the effect of this if I change a from 2 to 1/2? What's that going to do? What do you think that's going to do to the function? Multiplying by 2 stretched it so it was twice as high. What does multiplying by 1/2 do, do you think? Yeah, it squishes it. We could say it compresses it, right? Yeah, look what it did, right? Look what it did. So we end up now, instead of going over 2 and up 2, right? We could say that when I go over 2, the parent height is 2, right? We're going to multiply the parent height by the vertical dilation factor of 0.5. 2 times 0.5 is 1. So now the new height is shorter. When I go over 2, I only go up by 1. When I go over by 4, I normally go up by 4, but now I'm only going up by 1/2 of 4. Over 4 and up 2. So it squashed everything down vertically. Everybody see that? Okay. So again, I could, let's do this. Let me make the steps like, I just play this as a movie. Look what it does. As we increase a, it's just stretching, it's multiplying those heights by bigger and bigger values. When I decrease a, it's getting more squished because I'm multiplying them by smaller values. Okay? All right, give me 1 to 5 on that. Okay? All right, so let's see what we get here. So if I multiply by a, when a is a big number, when the absolute value of a is greater than 1, like 2, for example, what happened? I stretched it by a factor of a. Okay? What happened when I multiplied my function by a vertical dilation factor that's a fraction less than 1, between 0 and 1, like 1/2? I got to fix this. That shouldn't say stretch. It should say compress. Vertically compress by a factor of a. Okay? Now, what's going to happen if A is negative? Let's check that out. Okay, so if A is 2, we already saw that stretched it up by a factor, it multiplied all the heights by 2. Make a prediction for me. What do you think is going to happen if A is equal to, how about -1? How is that going to impact the parent function if I multiply the parent function by a vertical dilation factor of -1? Type that in chat for me. What do you think? I'm getting lots of people saying reflecting. Yeah, that's right. Look what happens. Let's look at why it's reflecting. How come? It follows the same rules we just established. Normally, I would go right by 1 and up by 1. So when I go right 1, my normal height, my parent height is 1, but I've got to multiply by my vertical dilation factor of -1. 1 times -1 is -1. So now I'm going right and up by -1, which is down by 1. Normally, I go to the right by 4 and up by 4, but I've got to multiply my normal parent height by -1. So now I go right 4 and up by -4, down 4. What's going to happen if I make A -2? What's going to happen there? Okay, I'm seeing a reflect and compress. What else? Anybody else got an idea? You guys tell me really quick, like what's going to happen to that point right there on my function? Let's pick that one where normally I would go over by 4 and up by 4. What's going to happen on my dilated function when the ant goes 4 to the right? Where's he going to go vertically? Where's he going to go vertically? Oh, that's not what I wanted. I want that. There we go. Okay, what's going to happen to that height? Normally when I go over 4, look at that. It's telling me that my height is going to be 4 normally, right? But in this case, look at the value of A. The number A that we're multiplying out front, the vertical dilation factor is -2, right? -2 is the vertical dilation factor. In math, a factor is something that we multiply, right? So I'm going to take my normal parent height and I'm going to multiply that by A. Well, what's A? That's the same thing as saying 4 times -2. 4 times -2 is -8, right? So shouldn't I now go over 4 and my new height is going to be -8 because when I multiplied my normal parent height by A, I got -8. So I go over 4 and down 8 to get to that point. Okay, everybody agree? Looks like a lot of people agree. Let's see what happens. Oh yeah, look at that. Okay, everybody see that? Okay. Oh, what happened there? There we go. Okay, so if I multiply by a negative value, then it's reflecting, in addition to stretching or compressing, it also reflects, right? So we've got these three numbers now, and we kind of know what they do. These three numbers, A is the vertical dilation factor, H is the horizontal translation, and K represents the vertical translation, right? A is the number that always gets multiplied by the function, so it's out in front being multiplied by the function. H is the number that is subtracted from X inside the function, and K is the number that's added to the function outside of the function. And we know what those three numbers do, okay, when we apply them now. So let's get a little practice here. So first of all, I want to know we've got this function f of x down here, right? We're going to practice just answering a few questions about functions. It's really important, I think, to really get this stuff and understand it well and understand it easily. You kind of have to scaffold your understanding. You got to start low and just work your way up. So we're starting here, first of all, with being able to do just these few things. I'm going to give you some examples, and I want you to tell me what is the parent function, and I want you to identify what are the number values of A, H, and K in our transformed function. So in this case, we've got this souped up function f of x here. That's it's a tricked out version of some really basic function. Well, what's the very basic function that we would have started with? If I get rid of all the numbers here, where did I start? What kind of function was that? Type it in chat for me, please. What was my basic parent graph? My parent function p of x. What was it for f of x? Before I transformed it with those numbers, what was it? Was it a square root graph? What was it? Absolute value. It was just absolute value, wasn't it? So my parent function was just the absolute value of x. And then I tweaked it by doing some things to it to change what the graph looks like, right? Okay. So what is the value of a in my new function, f of x? And remember, a is the vertical dilation factor, right? What is that? Type it in chat. What's a? Remember, a is the number that's multiplied by the function. You're multiplying by the function. So tell me, what's the number value of a in f of x? Yeah, it's negative 1/5, isn't it? Everybody agree? That's the number that's out front here. Maybe I should color code it like these. So that's green, isn't it? Right? So there's the value of a. It's what's being multiplied by the parent function, and it's negative 1/5. Well, if a is the vertical dilation factor, and it's negative 1/5, what's it doing to my parent, that V-shaped parent graph? What's it doing? Multiplying by negative 1/5 does what? The negative reflects it, correct? And the 1/5 compresses it. Everybody agree? So it's going to be compressed and reflected, okay? What about H? H is the horizontal translation, right? So there's H. It's the number that's being subtracted from X. What's the value of H in f of X? Type it in chat for me. Okay, I'm getting lots of similar answers. I'm getting 8s and negative 8s. Now I want you to think about this think about it this way. What value of H what would I have to plug in for H in order to get this result? In order to get X minus 8, what value would I have to plug in for H in my expression up there for f of X? Wouldn't I be plugging in an 8? Would everybody agree it's a positive 8? Okay. Yeah, it is, right? Because h is the number that's being subtracted from x. And so that's my h. It's equal to 8. Remember that the value of h is always going to be the opposite. Boy, this pen is so bad. Gosh. It's going to be the opposite of whatever that operation is between the x. If it's a subtraction, if we're subtracting 8, then h is positive. If we're adding 8, then h is negative. It's a little counterintuitive. That one's a little tricky. Okay. So if the horizontal translation, if the value of h is 8, then that means that we are going to the right by 8, doesn't it? Right? Because h is the amount that we're moving to the right. Positive 8 means to the right by 8. And then finally, what is k? So here's k, right? K is the number that's being added outside. Well, if I'm subtracting 2, isn't that the same as just adding a negative 2? Anybody agree? K is negative 2. And so that means that's my vertical translation. Translation just means slide or shift, right? So I'm going down by 2. Everybody agree? Those are the 3 things that are being done. Okay. So the question comes up then, probably you're trying to organize your thinking here, I bet, on this. You're probably starting to think, well, I'll tell you what, let's practice. Before we do anything else, let's practice this a little bit more. So I want you to stare at this for a second and see if you can tell me what is the parent function and what are the values of A, H, and K. Everybody try this on a piece of paper real quick. Okay, Anahi, what's the parent function here? If I were to get rid of all the fancy numbers there, what would I be left? Where did I start with this before I started tweaking it? What kind of function?
Absolute value.
Yeah, it's an absolute value, isn't it? Okay. What's the value of A here, Emily? Questions for Emily. What's the value of A?
I'm not sure.
Okay. Anybody got an answer to that? What's the value of A?
3.
Yeah, it's 3, isn't it? Good. A is the number. Remember, that's the value that's being multiplied outside, right? By our parent function. And so that's going to be a 3 this time, isn't it? There's the number that's being multiplied by the absolute value function is a 3. Okay, what about the K? Jade, what's the value of K here? Remember, K is the number that's being added to the function outside the function, right? So Jade, what's the value of K? How about Lindsay? What's the value of K? It's 1. Good. Okay, while you're at it, Lindsay, I'm going to challenge you. What's the value of H? 2. Good. Okay, because 2 is the number that's being subtracted from X, right? Notice once again here that the sign of H is the opposite of that minus, right? It's going to be a positive 2. Okay. All right, let's try another one here. How about this one? Let's see. Gabe, what's the parent function here? If I get rid of all the numbers, what's my parent function? Where did I start with this?
Get rid of all the numbers.
Yeah.
I'm not sure.
when I say get rid of the numbers, I mean if we just undo, if we don't worry about any of the transformations, what's the most basic kind of function that's in that family of functions right there, right? Where's our starting point? Is it well, okay, but it's p of x, but what's it equal to? Is it a square root of x? Is it an absolute value of x? What do we got going here? I don't see an absolute value here. So, what do you think? Anybody else got an answer for that?
Would it be x plus 1?
No, the plus 1, that's translating the function, right? We got to get rid of that plus 1. See, let's cross some things out here. That plus 1 is a horizontal translation, isn't it? And the multiplying by the negative 1/3 is a vertical dilation. So what are we left with if I get rid of the horizontal translation and the vertical dilation?
X squared.
Yeah, I'm just left with plain old x squared, aren't I? Right? So the parent function here, this is a quadratic, but here's the simplest form of a quadratic. Okay, so now we start with an x squared. To get f of x, we did some stuff to it. What do we do? What's the value of the vertical dilation factor a in this case? Isabella, can you tell me what a is? Questions for Isabella? Okay, how about Anahi?
Negative 1/3.
Negative 1/3. There you go. Okay. What's the value of h this time, Aurelia?
One.
Is it 1? Remember, h is the number, you got to be careful with this. H is the number that's being subtracted from x.
Negative 1.
Negative 1. There you go, right? And again, look at the fact that there's, h is going to be the opposite sign of the operation that's connecting the x and the 1. If it's an x plus 1, then h must be a negative 1 because it's the number that's being subtracted from x, right? That's the tricky one. Now, what about k this time? Olivia, what's the value of k here? That's the number that's being added outside the function.
I don't know. 0?
0, exactly. You're exactly right. It's 0 because there's nothing there, is there? If nothing shows up when there's a number that's being added or subtracted and it's invisible, it's got to be a 0, right? Because we don't write plus 0, we just leave that off, okay? Good. Another one. How about this one? Okay, first of all, I want the parent function. Aiden, what's the parent function here? Where would I start if I want to build f of x like it's shown there? Where do I start before I do any transformations? What kind of function are we dealing with?
Square root of x.
Yeah, square root of x. Good. Okay. There it is. So now we want the vertical dilation factor. What's being multiplied by the square root function, James? So what's being
multiplied by the square root?
Yeah, what number is being multiplied by the square root there?
Is it negative 7?
No, we're adding a negative 7. Let me ask you, I got a quick question for you, James. So say I gave you a line here. I'm going to write a line in slope intercept form. What's the slope of that line?
X.
No, it's not x. The slope, say it again.
1.
It's 1, isn't it? Because there's an invisible 1. The slope is always the coefficient of x, right? Whenever there's an invisible number in front of a number that's being multiplied, in front of a variable that's being multiplied, right? If a number doesn't show up and it's being multiplied, It's not a 0, it's a 1, isn't it?
Yeah.
Right? So there is, we don't write it because we don't really write, like we wouldn't say y equals 1 times x minus 3. We would just say x minus 3. We wouldn't say the 1 there, but technically there is a 1 in front of that radical, right? If nothing shows up, it's a 1. So the vertical dilation factor is 1, which just means that this square root function is not being dilated vertically, right? We're multiplying the heights by 1, which leaves them the same, okay? Everybody get that? Give me a thumbs up. People with cameras on, give me a thumbs up there so I can just, there we go. Okay, what's the value of h on this one? Let's see, I want the value of h Brogan.
Would it be -4?
It is -4. Good job, right? Because we're subtracting a -4 to get an x plus 4. Good job. And Brogan, what's the value of k?
-7.
You got it, -7. Okay, good. All right, I'm going to go through this one maybe just a little bit faster so we can get on. Everybody agree here that this is a weird function, but if I undid all of the transformations, the most basic function that I'm starting with in f of x is that log function we talked about the other day, right? You guys don't even know what the log function is or what it looks like. Well, you know what it looks like now, I guess, but you haven't even seen it before a couple days ago. But the point I want to make here is this transformation idea of starting with a basic function and transforming it, it works for everything, not just the functions you're familiar with, but all those other functions you've never even seen before. The same process is going to work when you get to them, okay? So what's the value of a, everybody? Just type it in chat. What are we multiplying our function by? 1/4, right, good job, it's 1/4. So that means it's not reflected, but it's compressed. Everybody agree? The heights are being multiplied by 1/4. Okay, what about, Alara, what's the value of h? It is 0, good job, right? Because there's nothing being subtracted from x, nothing shows up, so it must be 0. And then k, of course, is 5, isn't it? Okay. Then finally, what about this guy? This is another weird one, right? Well, if I undo multiplying my function by something and I'm going to cross out all the transformations here, right? There's my vertical dilation factor of 3. I'm multiplying 3 times my function. I'm subtracting 12 directly from x, so that's a horizontal translation. I'm subtracting pi from the whole thing, so that's a vertical dilation. If I get rid of all that stuff, what do I start with? Well, I just start with an exponential function, 2 to the x, right? Okay, and then we can see here that I'm multiplying out front by 3, so a is 3. I'm stretching this parent function vertically by a factor of 3. H is 12 because that's the number that's being subtracted from x, so I'm translating it to the right by 12. And I'm adding a negative pi, or I'm subtracting pi from the function, so I'm shifting it down by pi, okay? All right, so then is there an order in which I have to do these things? Well, you could follow the order of operations, right? Like if I've got this transformation of the parent function p of x here, well, following order of operations, we would first focus on the parentheses, right? So in the parentheses, we're subtracting h. So we would shift horizontally by h units first, maybe, if we're following order of operations. Then we would do, well, there's no exponents, right? Let's cross these off as we go here. So we already took care of parentheses. Whoops. We took care of parentheses. There are no exponents, but there is some multiplication. I'm multiplying the thing by a, right? So when we get to multiplication, that would be the next thing we do is vertically dilate the function. Okay, and if it's negative, we'd end up reflecting it also. And then finally, last step would be addition, subtraction. Yeah, we're adding k, and so the last thing we would do by order of operations is shift the function vertically. Okay, so that's one way that would work. Now, turns out though that all of these 3 transformations are independent of each other, and you can actually do them in any order that you choose. And we might come up with a better order than following PEMDAS. Okay, we'll try this out first and see if we can maybe make this a little bit easier. So let's try this example, okay? So we've got this example here where we have an absolute value function. Would you guys all agree here? We've already had quite a bit of practice on this. Would you agree that A is equal to negative 1/2 H is equal to negative 4, right? Got to be the opposite of whatever that is. So H is negative 4 and K is equal to positive 3. So what's that telling us? We should be squishing and reflecting the function vertically, right? We should be moving it negative 4 to the right. So we're going 4 to the left. And we're going, K is positive 3, so we're going to go up by 3. Well, let's do this in regular PEMDAS order first, right? So first we would do inside grouping symbols or parentheses. So first we're going to take care of the H being 4. So we're going to go left by 4. Everybody agree? Whoops. So, come on. There we go. So our first step is scoot it left by 4. Okay? Now what? Well, then the next thing we do is multiply, divide, right? So now we're going to take care of that negative 1/2 out front. So let's think what that is, right? That's our vertical dilation factor, okay? So this time, instead of going over by 2 by 2, so my normal parent height when I go to the right by 2 is 2. We're going to figure out how are we going to dilate that point. Where is it going to get stretched to vertically, right? Well, we're going to multiply the normal parent height by my vertical dilation factor of negative 1/2. Oh man, I didn't want to do that. I wanted to do, hang on, I'm going to tweak this a little bit. So normally we go, oh darn it. Normally we go, here we go, right 2 and up 2. But we're going to multiply that by A, which is negative 1/2. 2 times negative 1/2. Everybody agree that's negative 1? So my new height, instead of going over 2 and up 2, we're going to go over 2 and up 2 times negative 1/2. Right? We're going to go over 2 and up negative 1, so down 1. Ah, that's what we did, isn't it? Everybody with me? Okay. And then the last step was K is 3, so we should just shift this thing vertically by 3, right? Well, there it is. Okay. That's f of x, isn't it? Okay. We did all 3 of those things to it, and that's f of x. That's where we end up. Give me 1 to 5 on that. Okay, everybody weigh in on this, please, so I can kind of get a feel for where we are. Okay. Not bad. Not bad. I like it. Oh, you know what? We're about out of time. Okay, that's a good place to end for us, though. You can get started. This is practice. What is this? This is 3.2 practice 2, I think, right? So you guys could get a jump on this, but we'll continue to talk more about it next time. All right. Hey, real quick, before you guys go, I'm going to let you go here. Hey, Isabella, we need to get you situated with your Math Excel stuff. Could you stick around for just a second, and I'm going to get things figured out for you so we can get your account all set up. Everybody else, you guys go play in the snow. I guess you got to go to advisory first, but then you can go play in the snow. Have a great weekend. I'll be here after school if you need me. Go build a snowman. Maybe make a pie or something in the snow, like a math pie. Do something mathematical for me. Take a picture. All righty. See ya. Have a good one.